Question 1. The ester ethyl ethanoate, which is over here, undergoes hydrolysis under certain conditions as shown in the following chemical equation. A sample of 0.5 moles of the ethyl ethanoate is added to 0.5 moles of water in the presence of a catalyst to form a 500 centimeter cube solution in an inert solvent. And at equilibrium, we are going to have 0.175 moles of ethyl ethanoate. So the first part was calculate the concentration for all species present in the equilibrium mixture and give your answers to 3 significant figures. So let's write the equation again. We have CH3, COO, C2H5 plus H2O. It's a reversible reaction. We're going to form the acetic acid and the alcohol, which is ethanol. Now, first we have 0.5 moles of the ester and we have 0.5 moles for the water. We do not have anything for acetic acid, so here we're going to put 0 and 0. Now I'm going to work with the moles and then I'm going to divide by the volume to get the concentration of all of these species at the end at equilibrium. Now this will be, so first this is ICE. This is going to be minus x, plus x, and plus x, because these are going to increase the reaction because there's 0 at the beginning, so of course the reaction is going to shift this way. And at equilibrium, we're going to have 0.5 minus x, 0.5 minus x, x, and x. Now they said that at equilibrium, we're going to have 0.175 of the ethyl ethanoate that's going to be present. Therefore, I'm going to put 0.5, which is 0.5 minus x of this one, to find the x, is going to be equal to 0.175 at equilibrium. Therefore, the x is going to be equal to 0.325. Now, I have the number of moles for the ethyl ethanoate and for the water, and they are equal to 0.325 at equilibrium, and this will be also 0.325. I'm sorry, this will be actually 0.5 minus x, so it's going to be 0.175, and this is going to be 0.175. However, the x over here is going to be equal to 0.325. So now we can work and divide by the volume. So we are going to get the CH3, COO, C2H5. The concentration is equal to the concentration of H2O, which is equal to the number of moles over the volume, equal to 0.175 over the volume, which is, so the volume was it was actually 500 centimeter cube, and I'm going to change it to liter. So it's going to be equal to 0.5 liters or decimeter cube, 0.5 decimeter cube. And then, so I'm going to divide over here by 0.5, and the concentration is going to be equal to 0.350 m. And we have to add a 0 over here because they want the final answer to be to 3 significant figures. Now for the acetic acid and for the ethanol, they also have the same number of moles. So we're going to put CH3 COOH is equal to C2H5OH, and they're both going to be equal to the number of moles over the volume, and their number of mole is 0.325 over 0.5, and the answer is going to be 0.650 m. This is for the concentration of the acetic acid and the alcohol, which is going to be 0.650, and we have to add a 0 because they need the answer to 3 significant figures. Now they ask us to calculate the value of the equilibrium constant expression Kc and give your answer to 3 significant figure. So for Kc, it's going to be equal to the products over the reactants, and the reactants are the ethyl ethanoate and the water. And we're just going to substitute. So the concentration for the products 0.650, we're going to multiply them together, so it's going to be 0.650 squared over the concentration of the reactants, which were 0.350, so it's going to be 0.350 squared, and the answer is going to be 3.4489. However, they need the answer to 3 significant figures, therefore it's going to be 3.45, as we're going to round this number up, which is the 4, because we have an 8 which is greater than 5. So this is the final answer for KC. Question 2. Hydrogen chloride undergoes a reversible reaction with oxygen. This is the reaction taking place, and the reaction is carried out at a temperature of 400 degrees Celsius in the presence of a copper chloride catalyst. So the catalyst is solid, and these are all gases, so the catalyst is heterogeneous. Now they said calculate delta H of the reaction, given that the enthalpy change of formation of HCl gas and H2O gas in kilojoules per mole are minus 92 and minus 242 respectively, and give your answer to 3 significant figures and include the sign. Now I just have to note something, that the enthalpy change of formation is the enthalpy change when we form 1 mole of a certain compound from its elements under the standard state conditions. So it is the enthalpy change when 1 mole of a compound is formed from its elements in their standard state and under the standard conditions. And you just have to note that they gave you only the enthalpy change of formation for HCl and H2O. They did not give you the enthalpy change of formation of O2 and Cl2. And this is because the enthalpy of formation of O2 and Cl2 is equal to 0, because elements in their standard state, they have an enthalpy change of formation equal to 0, because you are not forming them from anything else. They're just like a reference point. So their enthalpy change is going to be equal to 0. However, for H2O and HCl, which are compounds, these values are given. However, you need to multiply them by the coefficient, which is for the H2O, which was 2, and for the HCl, which was 4. So we need to calculate the delta H for the reaction, and the formula for the delta H of the reaction is equal to the total delta H formation of the products minus the total delta H formation of the reactants. And the product is water. So we have water over here, and it was given as minus 242. However, we need to multiply it by 2 because we have this, the molar coefficient. So we need to use molar coefficient. So it's going to be 2 multiplied by minus 242 minus 4 times the value of HCl. Delta H formation of HCl was 92. And the answer is going to be minus 116. And the unit is kilojoules per mole. So this is the answer for the delta H of the reaction, and they need the answer to 3 significant figures. Now, for the other part, they said that when 2 moles of HCl are mixed in a sealed container with 0.65 moles of O2 at a specific temperature, 0.6 moles of H2O are formed, and the total pressure inside the container is 1 times 10 to the power 5 Pascal. They said calculate the total number of moles of gases at equilibrium and give the answer also to 3 significant figures. So to calculate the total number of moles, I'm going to use an ice table. So first I'm going to write the reaction again, which is for HCl plus O2. And I'm going to work with the moles, 2Cl2 plus 2H2O. First, we have 2 moles for HCl, and we have 0.6 moles for the oxygen, and we do not have anything at the beginning for H2O nor for Cl2. Now this is going to be for the equilibrium, the number of moles for at equilibrium for H2O. So we're not going to include it in the initial number of moles. So we're going to have 2 moles over here, 0.6 moles, 0 and 0. Then we're going to put over here a minus 4x. We just put the ICE, minus 4x, and then we're going to put 2 minus 4x minus x, 0.6 minus x, plus 2x over here. And then it's going to be 2x. And here we're going to put plus 2x. And here it's going to be also 2x. So as you can see, the positive sign was over here because the reaction is going to shift this way as the number of moles initially were actually 0. Now, one thing they said is that the 0.6 moles of H2O are formed, and they mean by this that the 0.6 moles of H2O are formed at equilibrium. So I'm going to put 2x is equal to 0.6, so x is equal to 0.3 moles. Now I can use the x to get the values for the HCl, the number of moles at equilibrium, and for O2. So for HCl, it's going to be, the number of moles of HCl is 2 minus 4x. So it's going to be equal to 2 minus 4 multiplied by 0.3. And it's going to be 0.8 moles for this one. So here we're going to have 0.8 moles. Now for the O2, it's 0.6 minus x, so it's actually equal to 0.6 minus 0.3, it's 0.3 moles. For the Cl2 and the H2O, they're both going to be equal to 0.6, and this is 0.6. So the total number of moles is going to be equal to the HCl, which we got as 0.8, and we add the number of moles for O2, which was 0.3, and we need to add the 0.6 for Cl2 and 0.6 for H2O, and we get a total number of moles which is 2.30, because they need the answer to 3 significant figures. Now for the other question, they said calculate the mole fraction of each of the gases at equilibrium and give your answer to 3 significant figures. Now to get the mole fraction, we need to use this formula, which is x is equal to the number of moles over n total. First, I'm going to find the mole fraction for HCl. The moles for HCl is 0.8, which we found before, and the total number of moles is 2.3. We're going to get an answer of 0.3478. To 3 significant figures is going to be 0.348. The mole fraction for O2 is 0.3 divided by 2.3. It will be 0.1304, and we round it to 3 significant figures, so 1, 2, 3, it's going to be 0.130. The mole fraction for Cl2 and for H2O is going to be the same. It's 0.6 divided by 2.3, and it's going to be equal to 0.26086, so it's going to be equal to 0.261 to 3 significant figures. So we got the mole fraction for HCl, O2, for H2O, and for the Cl2. So we finished this part. Now for the final part, we have to calculate the value of Kp, and we need to write the unit, and you need to give your answer in scientific notation to 3 significant figures. Now for Kp, it's going to be equal to, so I'm going to erase this part. So Kp is going to be equal to the pressure of H2O squared multiplied by the pressure of Cl2 squared divided by the pressure of HCl to the power of 4 multiplied by the pressure of O2. And I raised the H2O and the Cl2 to the power of 2 and HCl to the power of 4 because of the molar coefficient. Now let's first determine the unit that for Kp that we are going to use. So if H2O is Pascal squared and the Cl2 is Pascal squared, and then for HCl it's going to be Pascal to the power of 4, and for the O2 it's going to be Pascal. So therefore we're going to end with a unit that is Pascal to the power of -1. Now let's find the pressure for each gas. So for the pressure of Cl2, we're going to use, to find the pressure, we're going to use this formula, which is the partial pressure is equal to the mole fraction, which we found in the part before, and we're going to multiply it by P total. And P total is equal to 1 times 10 to the power of 5 Pascal. So therefore, to find the pressure of H2O, we're going to use this formula. But since we have the mole fraction for Cl2 and for H2O, so we got the mole fraction for Cl2 and H2O is going to be the same. Therefore, the pressure of H2O and the pressure of Cl2 is also going to be the same, as they have the same mole fraction. So it's going to be equal to their mole fraction, which was actually 0.261, which we got before. And we're going to multiply it by the P total. So the answer is going to be 26,100 Pascal. And then we find the pressure for HCl, which is going to be the mole fraction of HCl multiplied by P total, and we're going to get the answer 0.348 multiplied by 1 times 10 to the power of 5, and it's going to be 34,800 Pascal. And for the pressure of O2, it's going to be the mole fraction of O2 multiplied by P total. So it's going to be 0.130 multiplied by 1 times 10 to the power of 5. And the answer is going to be 13,000 Pascal. Now we just have to plug these values over here and to find the Kp. So Kp is going to be equal to 26,100 squared multiplied by 26,100 to the power 2 divided by 34,800 power of 4 multiplied by 13,000, and we're going to get the Kp as 2.43 times 10 to the power of minus 5, and we need to include the unit which we found before as Pascal to the power of minus 1. Question 3, consider the following reversible reaction. So we have this reversible reaction, and they said calculate the equilibrium concentration of O3 in mole decimeter to the power minus 3 if the equilibrium concentration of O2 is 0.062 mole dm to the power minus 3. So we have the value for Kc, and Kc is products over reactants. So we only have one unknown, which is the O3, so we can use it immediately to find the value for the concentration of the O3. So Kc is equal to O3 to the power of 2. This is because it has a coefficient of 2 divided by the O2 to the power of 3. Now we're going to get a value for O3 squared. It's going to be Kc, which is 1.8 times 10 to the power minus 7, multiplied by 0.062 to the power of 3, which is over here. And we're going to get a final answer for the concentration of O3 as 6.5497 times 10 to the power of minus 6. So if they need the answer to two significant figures, then it's going to be 6.5 multiplied by 10 to the power of minus 6, and this is the concentration for O3 at equilibrium. Now for the next part, they said without calculation, give the concentration of O2 that's going to be initially. So we don't have to do any calculation for this part. As you can see, the Kc is very, very small. It's 1.8 times 10 to the power minus 7. So only a very small amount of O2 is going to decompose, as the reaction is not very favored. So therefore, the initial concentration of O2 is actually going to be the same almost at the end, because we're not going to have a lot of O2 decomposing. Therefore, the O2 initially is going to be 0.062 m. Now, question 4, consider the following endothermic reversible reaction that takes place in a closed flask. The composition of an equilibrium mixture is determined where the concentration of Y in mole dm to the power minus 3 is 3 times the concentration of X, where X at equilibrium, the equilibrium concentration of X, is equal to 1 m. Now they asked us to calculate the value of Kc and to give the answer to two significant figures. So Kc is going to be equal to Y to the power of 3 due to having a coefficient of 3 over the concentration of X. So it's actually Y to the power of 3 over X. Now, to find the value of Kc, we know that Y is equal to 3 times the concentration of X. So if I substitute Y by this, which is 3X, and I raise it to the power of 3, and here I'm going to put also X. Now we know that X is equal, at equilibrium is equal to 1 m, therefore it's going to be 3 to the power of 3 over 1, so it's going to be equal to 27. Therefore, Kc is going to be equal to 27, and these are going to be two significant figures. Now, they said in the Next question, that we need to determine the values of Z and W in the unit of Kc, which is mole dm, and we have to know the value for Z and W, and to give your answer as an integer, and do not forget to include the sign in your answer. So first I have to find the unit for the Kc. So Kc is m to the power of 3 over the concentration of x, which is m. So if I cancel, I'm going to get m squared. Now m is equal to mole dm to the power minus 3. So I'm going to plug it over here. So it's going to be mole dm minus 3 raised to the power of 2. And it's going to be mole to the power of 2 dm minus 6. Now therefore, the z is going to be equal to 2. And the w is going to be equal to minus 6.